Welcome, and thanks for being here. You can get comfortable. There's nothing you need to do right now. No need to focus too much. Just let the words be in the background. Some thoughts might catch your attention, others might drift away, and that's perfectly fine. If you enjoy this kind of calm space, you can leave a like to support the channel and subscribe if you'd like to come back again. It really helps, and it keeps this space going. For now, just take it easy. Let the sound settle, let the day fade a little, and allow yourself to rest. When we speak about a black hole, we are not describing a solid object in the ordinary sense, but rather a region of space where gravity becomes so strong that the usual behavior of matter and light reaches extreme limits. And this matters because many common images of black holes, such as giant holes or dark tunnels, quietly mislead the imagination, while in physics, a black hole is better understood as a particular way that space and time become curved by a very large concentration of mass. And from this perspective, a black hole is not something added to the universe, but something that naturally emerges when gravity overwhelms the forces that normally resist collapse. And the defining feature of a black hole is the presence of a boundary called the event horizon, which marks the region beyond which signals can no longer reach distant observers. And this boundary is not a physical surface, but a point of no return in space-time, where all possible paths forward lead inward rather than outward. And this is why black holes are described as hiding things, because events that occur beyond this boundary become inaccessible to the outside universe. And hidden in this context does not mean destroyed, but simply unavailable to observation. And it is also useful to note that black holes do not behave like cosmic vacuum cleaners, because at large distances, their gravitational influence is no different from that of any other object with the same mass. And if a black hole were to replace a star like the Sun, planets could continue orbiting in nearly the same way. And this tells us that the true strangeness of black holes is not found in their distant effects, but in the behavior of space and time very close to their center. And historically, black holes were first encountered through mathematics, appearing as solutions to Einstein's equations long before any observational evidence existed. And over time, observations of stellar motion, radiation from hot gas, gravitational waves, and direct imaging have steadily confirmed their reality, giving us strong confidence that black holes exist even though their interiors remain beyond direct reach. And according to current theory, the center of a black hole contains something called a singularity, a region where density and space-time curvature become extremely large, and our equations no longer provide reliable descriptions. And in physics, such breakdowns are usually interpreted as signs that a deeper theory is needed, rather than as literal infinities. And for this reason, when we ask what black holes really hide, we are partly asking what lies beyond the limits of our present understanding. And black holes also occupy a special position in science because they sit at the intersection of general relativity and quantum mechanics. And these two theories do not yet fit together seamlessly, and black holes provide some of the clearest situations where this tension becomes unavoidable. And at the most basic level, what black holes hide are regions of space-time where observation and prediction gradually fade. And as we move forward, we will explore how black holes form, how their boundaries behave, and how matter, energy, and information interact with them, building slowly toward a clearer picture of what may be happening behind the veil of gravity. Black holes do not appear suddenly or in isolation, but form through natural processes that unfold over long periods of cosmic time. And understanding how they form provides an important foundation for understanding what they may later contain or hide, because formation shapes structure, and structure influences behavior. And the most common pathway to black hole formation begins with very massive stars, stars that contain many times the mass of our Sun. And throughout most of their lives, these stars exist in a balance between outward pressure produced by nuclear fusion in their cores and inward gravitational attraction produced by their own mass. And as long as fusion continues, this balance remains stable. But when the star exhausts its fuel, the outward pressure weakens, gravity begins to dominate, and the core collapses inward. And this collapse can occur extremely quickly on astronomical timescales. And in many cases, it is accompanied by a supernova explosion that ejects the star's outer layers into space, while the core continues to contract. And if the remaining core is massive enough, no known force is able to halt this contraction, and a black hole forms. And this process shows that black holes are not separate from stars, but represent one possible final stage of stellar evolution. And not all black holes form from single stars, because at the centers of most galaxies reside supermassive black holes with masses millions or billions of times greater than the Sun. And these enormous objects are thought to grow gradually by pulling in gas, dust, stars, and by merging with other black holes. And this slow accumulation means that supermassive black holes contain a long and complex history of absorbed matter and energy. And from the outside, however, once matter crosses the event horizon, it becomes part of the black hole's total mass, charge, and spin. And these three properties are all that remain observable to distant observers, regardless of the complexity of what fell in. And this simplicity suggests that much detailed information about infalling matter becomes hidden behind the horizon, even though its mass and energy still influence the black hole's gravity. And it is also important to note that black holes do not form instantaneously with sharp boundaries, but develop dynamically as collapse proceeds. And the event horizon itself grows as matter falls inward. And this gradual formation means that black holes are evolving regions of space-time rather than static containers. And recognizing this helps frame later questions about what may be happening inside, because whatever black holes hide must emerge from physical processes that begin with ordinary matter, shaped by gravity into increasingly extreme states. Gravity is the force that shapes black holes. Yet gravity itself is often misunderstood, because in everyday experience it feels simple, like a steady pull toward the ground, while in modern physics, gravity is understood as a curvature of space and time caused by mass and energy. And this way of thinking becomes especially important near black holes, where curvature grows so strong that space and time behave in ways that have no everyday analogy. And as an object approaches a black hole, it is not being pulled inward by a mysterious force, but is instead following the natural paths allowed by curved space-time. And these paths gradually tilt inward as curvature increases, making outward motion more and more difficult and eventually impossible beyond the event horizon.
And this perspective helps explain why black holes are not surrounded by invisible walls or sudden barriers, but by smoothly changing geometry that quietly guides motion inward. And as gravity strengthens near a black hole, differences in gravitational strength across small distances become significant, and this produces tidal forces, meaning that different parts of an object experience slightly different accelerations. And over time, these differences stretch and compress objects, and near smaller black holes, these tidal forces become extremely strong, while near very large black holes, they may be gentler at the horizon. And another consequence of intense gravity is the slowing of time relative to distant observers, because clocks closer to massive objects tick more slowly than clocks farther away. And near a black hole, this time dilation becomes very pronounced. And from the perspective of a distant observer, an infalling object appears to slow down and gradually fade as it approaches the event horizon, while from the perspective of the infalling object, its own time flows normally and it crosses the horizon without noticing any sudden change. And this difference in perspectives does not represent a contradiction, but reflects the relativity of time in strong gravitational fields. And this has important implications for what black holes hide, because events that occur inside the horizon may happen in finite time for the infalling observer, yet remain forever hidden from the outside universe. And as gravity continues to increase deeper inside, familiar ideas such as distance and duration become harder to define in ordinary terms. And this gradual loss of intuitive meaning marks the transition from regions we can describe confidently to regions where theory becomes uncertain. And in this way, gravity near black holes does not merely pull things inward, but reshapes the framework within which physical events unfold, preparing us to explore what happens closer to the boundary itself.
The boundary that defines a black hole more than any other feature is known as the event horizon, and this boundary marks the point beyond which signals can no longer reach distant observers. And although it is often imagined as a physical surface, it is more accurate to think of it as a location in space-time where the structure of possible paths changes in a fundamental way. And outside the event horizon, it is always possible, at least in principle, for light or matter to move outward, while inside the event horizon, every possible future path leads deeper inward and none lead back out. And this does not occur because of a sudden physical barrier, but because space-time itself becomes increasingly tilted toward the center of the black hole. And this geometric interpretation is important because it explains why crossing the event horizon does not require infinite energy and does not involve a violent local event. And in simple theoretical models, an observer falling freely toward a sufficiently large black hole would not notice anything special at the exact moment of crossing. And this quietness can feel counterintuitive because the horizon represents such a dramatic limit from the outside, and yet locally it may feel ordinary. And from the perspective of a distant observer, however, the situation appears very different, because as an object approaches the horizon, the light it emits becomes increasingly redshifted and delayed, making the object appear to slow down and gradually fade. And this visual effect creates the impression that the object never quite crosses the horizon, even though from its own perspective it does.
And this difference in viewpoints is not a contradiction, but a consequence of how time and light behave in curved spacetime. And it highlights an important idea that black holes hide events rather than objects, meaning that what becomes inaccessible is not the existence of matter itself, but the future history of that matter. And once a signal can no longer escape, whatever happens afterward cannot be communicated outward. And this leads to a subtle shift in how we think about hiding, because it is not that black holes actively conceal things behind a physical curtain, but that the geometry of spacetime prevents information from traveling back. And it is also useful to note that the size of the event horizon depends on the mass of the black hole, with more massive black holes having larger horizons. And this means that the horizon of a supermassive black hole can span distances comparable to the orbit of planets, while the horizon of a stellar mass black hole may be only a few tens of kilometers across. And yet, despite these differences in scale, the fundamental role of the horizon remains the same, acting as a one-way boundary between regions that can exchange information and regions that cannot. And understanding this boundary provides a foundation for exploring what happens near it and gradually what may lie beyond it. As an object moves closer to the event horizon, the environment around it changes gradually rather than suddenly. And this gradual change is important because there is no sharp physical line in space where ordinary physics instantly disappears, but instead a smooth progression toward more extreme conditions. And far from the black hole, gravity behaves in familiar ways, guiding motion much like gravity around stars or planets. But as distance decreases, gravitational effects become stronger, and the curvature of space-time becomes more pronounced. And one of the first noticeable changes is the stretching of space in the direction toward the black hole's center, while space in sideways directions becomes compressed. And this unequal stretching and squeezing produces tidal forces, meaning that different parts of an object experience slightly different accelerations. And over time, this causes objects to become elongated and distorted. And the strength of these tidal forces depends on the mass of the black hole, with smaller black holes producing extreme tidal forces farther out, while very large black holes produce gentler tidal forces near the horizon. And this means that approaching the horizon of a supermassive black hole could, in principle, feel relatively calm at first. And another important change involves light, because light climbing out of a strong gravitational field loses energy, causing its wavelength to stretch. And as an object falls closer to the horizon, the light it emits becomes increasingly redshifted when seen from far away, eventually shifting beyond detectability. And time behavior also changes, because clocks closer to the black hole run more slowly compared to clocks far away. And this time dilation becomes stronger as distance decreases. And together, these effects shape how black holes hide processes, not by sudden destruction, but by making them increasingly difficult to observe, until finally observation becomes impossible. Light plays a central role in how black holes appear to us, because nearly everything we learn about the universe arrives in the form of light. And when light interacts with strong gravity, its behavior changes in quiet but important ways. And near a black hole, these changes become especially significant. And one of the key effects is gravitational redshift, which occurs when light loses energy while climbing out of a deep gravitational field. And as light loses energy, its wavelength becomes longer, shifting toward the red end of the spectrum. And for light emitted close to the event horizon, this redshift becomes extreme, meaning that even high-energy light can be stretched into wavelengths that are very difficult or impossible to detect. And this gradual weakening of escaping light contributes to the appearance that the region near the horizon is dark, not because nothing is happening there, but because the signals cannot reach us effectively. And light is also affected in its path, because strong curvature bends the trajectories that light follows. And near a black hole, light can orbit temporarily, spiral inward, or be deflected at large angles. And this bending shapes the appearance of the black hole's surroundings, producing rings and distortions in the light from nearby matter. And these visual effects allow astronomers to infer the presence of black holes, even though the interior itself cannot be seen. And another important consequence is that light emitted from matter falling inward becomes increasingly delayed, so that successive signals take longer and longer to reach distant observers. And over time, this makes infalling objects appear to slow and fade. And this visual fading does not mean the object has stopped, but reflects how time and light behave in curved spacetime. And in this way, light traces the boundary between what can be observed and what cannot, and it quietly marks the limit of access created by the event horizon. And understanding how light behaves near black holes helps clarify that darkness is not an absence of activity, but a consequence of gravity shaping the flow of information. Inside and outside a black hole are not separated by a physical wall, but by a difference in how space-time is arranged. And this difference creates two very distinct perspectives on the same region. And from far away, a black hole appears as a stable object with a clear boundary, while from the viewpoint of something falling inward, the experience is very different. And this contrast arises because time and space do not behave in the same way for all observers. And near a black hole, these differences become especially pronounced. And from the perspective of a distant observer, an infalling object appears to approach the event horizon more and more slowly, and the light it emits becomes increasingly redshifted and delayed, making the object appear to fade. And this creates the impression that the object never quite crosses the horizon, while from the perspective of the falling object, its own time flows normally, and it crosses the horizon after a finite amount of time without encountering a sudden barrier. And both descriptions are correct within their own frames of reference. And this duality highlights the idea that black holes hide events rather than objects, because the crossing of the horizon does occur, but it cannot be witnessed from the outside. And once the horizon is crossed, all future motion inevitably leads deeper inward, and the outside universe can no longer receive signals from that region. And this separation creates an inside that is causally disconnected from the outside, meaning that no influence can travel from the interior back to distant observers. And it is important to note that inside the horizon, the roles of space and time become subtly altered, in the sense that moving inward becomes as unavoidable as moving forward in time. And just as we cannot stop time from progressing, an object inside the horizon cannot avoid moving toward the center. And this change in structure does not require any additional force, but follows naturally from the geometry of spacetime. And this geometric viewpoint helps remove some of the drama from common descriptions of black holes, replacing it with a quieter picture of inevitable motion guided by curvature. And understanding this difference between inside and outside perspectives prepares us to consider what kinds of physical processes may still occur inside, even though they remain hidden from external view.
Time behaves in unusual ways near black holes, and this behavior is not an illusion or visual trick, but a direct consequence of how gravity influences space-time. And in everyday experience, time feels steady and uniform, but in physics, the rate at which time passes depends on both motion and gravitational strength. And near very massive objects, time runs more slowly compared to regions farther away. And near a black hole, this effect becomes extreme. And as an object approaches the event horizon, clocks closer to the black hole tick more slowly relative to clocks far away. And from the perspective of a distant observer, processes near the horizon appear stretched out, taking longer and longer to unfold. And this is why an infalling object seems to slow as it approaches the boundary. And yet, from the perspective of the infalling object itself, its own clock continues to tick normally, and it crosses the horizon after a finite amount of time. And this difference does not represent a contradiction, but reflects that time itself is not absolute, and each observer measures time according to their own path through space-time. And deeper inside the black hole, the structure of space-time becomes even more unfamiliar, and directions that once represented spatial movement gradually take on a time-like character, meaning that movement toward the center becomes unavoidable in the same way that movement toward the future is unavoidable outside. And this idea can be difficult to visualize, but it expresses a simple point, that inside a black hole, the concept of staying in one place no longer applies in the usual sense. And time near black holes therefore plays a central role in what is hidden, because events that occur inside may take place within ordinary amounts of time for infalling observers, yet they remain permanently outside the timeline of distant observers. And this separation between timelines contributes to the quiet mystery of black holes, not because time stops or breaks, but because time unfolds differently depending on where one is located. And recognizing this prepares us to think more carefully about what might happen deeper inside, where space-time curvature becomes stronger and our familiar intuitions gradually lose their reliability.
As gravity grows stronger near a black hole, the differences in gravitational pull between nearby points in space become more pronounced, and these differences produce what are known as tidal forces, meaning that separate parts of an object experience slightly different accelerations, and in everyday situations, these differences are extremely small, but near a black hole, they can become very large. And this leads to stretching and squeezing effects that gradually distort the shape of falling objects. And along the direction toward the black hole's center, objects tend to be stretched, while in sideways directions they tend to be compressed. And over time, this combination of stretching and compression can become severe. And this process is often informally called spaghettification, though in physical terms, it is simply the result of uneven gravitational forces acting across space. And the strength of these tidal forces depends strongly on the mass of the black hole. And near smaller black holes, they become intense at relatively large distances, while near supermassive black holes, they may remain mild until very close to the horizon. And this means that the local experience of falling toward a black hole depends not only on distance, but also on the size of the black hole itself. And these tidal effects play an important role in shaping what matter becomes as it falls inward, because atoms, molecules, and larger structures cannot maintain their usual configurations under extreme stretching, and bonds between particles are eventually overcome, and matter is gradually transformed into more fundamental forms. And this transformation does not happen all at once, but unfolds gradually as gravitational differences increase. And from an external viewpoint, however, much of this internal transformation remains hidden, because the signals that would describe it become increasingly redshifted and delayed. And in this way, tidal forces contribute not only to the physical breakdown of matter, but also to the concealment of that breakdown from distant observers. And understanding this slow progression helps clarify that black holes do not instantly destroy objects at their boundaries, but instead subject them to increasingly extreme conditions as they move inward.
When matter begins to fall toward a black hole, it does not usually travel inward in a smooth, silent plunge, but often forms a rotating structure known as an accretion disk. And this disk arises because infalling matter typically carries angular momentum, meaning it has some sideways motion rather than moving straight inward. And as this matter spirals closer to the black hole, friction and collisions within the disk cause energy to be released. And this energy is emitted in the form of radiation, making the region around the black hole extremely bright. And in many cases, this radiation is more luminous than the combined light of all the stars in a galaxy. And this brightness is one of the main ways astronomers detect black holes, even though the black holes themselves do not emit light. And as matter continues to lose energy within the disk, it gradually moves inward, approaching the event horizon. And during this inward journey, the physical state of the matter changes, because temperatures rise to millions or even billions of degrees, and atoms become fully ionized, meaning their electrons are stripped away, leaving a hot plasma. And this plasma is influenced by strong magnetic fields that can shape its motion and behavior. And some of this energized material is redirected into narrow streams called jets that shoot outward along the black hole's rotation axis. And these jets can extend for enormous distances, far beyond the size of the black hole itself. And while jets and disks are external phenomena, they are closely connected to what falls inside, because they represent how energy and angular momentum are redistributed before matter crosses the horizon. And once matter passes beyond the event horizon, however, it can no longer contribute to observable disks or jets. And from the outside, all that remains is the black hole's increased mass and altered spin. And this transition marks another stage in how black holes hide complexity, because detailed processes in the disk lead to a simple change in a few global properties. And understanding how matter behaves before crossing the horizon helps clarify what information is lost to observation and what information remains accessible.
As matter moves inward toward a black hole, it becomes increasingly compressed, not in the sense of being packed into a rigid container, but in the sense that gravity forces particles into ever smaller regions of space. And this compression raises both density and energy, and at extreme levels, matter no longer behaves in ways described by ordinary solid, liquid, or gas states, and instead enters regimes that can only be described using high-energy physics. And in the outer regions near a black hole, matter exists primarily as plasma, a hot mixture of free electrons and atomic nuclei.
But as matter continues inward, even these familiar distinctions begin to lose meaning, and the separation between individual particles becomes less well defined, and quantum effects become increasingly important. And one way to think about this process is not as a sudden crushing, but as a gradual loss of structure, where larger arrangements break down into smaller components, and those components are forced into closer proximity. And this progressive breakdown means that objects do not remain recognizable as they approach the core, and instead are transformed into streams of energy and elementary particles. And from an external perspective, however, these internal changes cannot be directly observed once they occur close enough to the horizon, because the signals that would describe them become increasingly redshifted and delayed, and eventually unreachable. And this again illustrates how black holes hide processes rather than simply removing matter. And another important aspect of compression is that energy itself contributes to gravity, meaning that as matter becomes more energetic, it further strengthens the gravitational field, creating a feedback effect that drives collapse even more strongly. And this feedback does not lead to explosive outward motion, but to continued inward focusing. And while current theories can describe this process reasonably well outside the horizon, they struggle to describe what happens when densities become extreme near the center. And this limitation reminds us that descriptions of the deepest interior remain uncertain. And at this stage, it is enough to recognize that matter falling into a black hole does not simply vanish, but undergoes a sequence of transformations that progressively remove its familiar structure, while its mass and energy continue to shape the black hole as a whole.
Physics provides powerful tools for describing how black holes influence their surroundings. But these tools have clear boundaries, and understanding what physics can describe is just as important as understanding what it cannot. And outside the event horizon, the equations of general relativity offer precise predictions about the motion of matter, the bending of light, and the flow of time. And these predictions have been confirmed by many observations, giving us strong confidence in their accuracy. And within this framework, black holes are characterized by a small set of measurable properties, including mass, rotation, and electric charge. And these quantities determine how the black hole interacts with the rest of the universe. And physics can also describe how accretion disks form, how jets are launched, and how gravitational waves are produced when black holes merge. And all of these phenomena occur outside the horizon, where information can still reach us. And inside the event horizon, however, the situation changes. Because although general relativity still provides mathematical descriptions of spacetime, these descriptions lead to extreme conditions where curvature grows without bound. And at the center, the theory predicts a singularity, a region where physical quantities become infinite. And infinities in physics usually signal that a theory is being pushed beyond its domain of validity, rather than that reality itself contains literal infinities. And this suggests that general relativity alone is not sufficient to fully describe black hole interiors. And quantum mechanics, which successfully describes matter at very small scales, must also be taken into account. And yet, a complete theory that unifies gravity and quantum mechanics does not currently exist. And as a result,
physics cannot reliably describe what happens at the deepest levels inside a black hole. And this limitation does not mean that nothing can be said, but it does mean that any statements about the core involve uncertainty. And at this stage, it is important to distinguish between well-tested predictions about regions near and outside the horizon, and more speculative ideas about what may lie beyond. And this distinction helps keep our exploration grounded, because it reminds us that black holes hide not only matter and events, but also the limits of our present theories.
When physics reaches the edge of what it can reliably describe, it does not stop, but instead reveals where deeper understanding is needed. And black holes represent one of the clearest examples of this boundary. And inside the event horizon, our best theories continue to produce mathematical results, but those results become increasingly difficult to interpret physically. And one reason for this difficulty is that general relativity treats spacetime as smooth and continuous, while quantum mechanics suggests that at very small scales, nature may have a discrete or fluctuating structure. And near the center of a black hole, where densities and energies become extreme, both descriptions are likely relevant, yet they do not naturally fit together. And because of this mismatch, different theoretical approaches propose different possibilities for what may exist inside, and none of these possibilities have yet been confirmed. And some models suggest that the singularity predicted by general relativity may be replaced by a region of extremely dense but finite matter, while others propose that space-time itself undergoes a phase change, similar in spirit to how water changes into ice, though at a far more fundamental level. And there are also ideas in which the interior structure depends on quantum entanglement, or where information is distributed across the horizon rather than stored at a central point. And while these ideas differ in their details, they share a common theme, that the simple picture of an infinitely dense point is likely an approximation rather than a literal description. And it is important to approach these ideas with caution because they are not yet supported by direct evidence, and their value lies primarily in guiding future theoretical work. And at this stage, what can be said with confidence is that current physics cannot provide a complete description of black hole interiors. And this gap in understanding is itself part of what black holes hide, because they conceal not only physical processes, but also the shortcomings of our existing models. And recognizing this limitation does not weaken science, but strengthens it, because it clearly marks where progress is needed. And as we continue, we will explore specific questions that arise from this uncertainty, including whether information can be truly lost inside a black hole, or whether it must somehow be preserved. One of the most well-known ideas associated with black holes is the concept of a singularity. And in simple terms, a singularity is a region where density and space-time curvature become extremely large, according to the equations of general relativity. And this result emerges naturally when the theory is applied to collapsing matter. And yet, it is important to understand that singularities are not objects in the usual sense, but rather indicators that the mathematical description has reached a point where it can no longer provide meaningful predictions. And in physics, this usually suggests that a deeper or more complete theory is required. And the singularity, therefore, represents a boundary of knowledge rather than a confirmed physical structure. And in the simplest models of black holes, the singularity is described as a point at the center,
while in rotating black holes it may take the form of a ring. And these differences arise from how rotation affects spacetime geometry. And regardless of the specific shape, the key idea is that inside this region, the familiar concepts of distance, time, and causality lose their usual meanings. And this makes it difficult to say what it means for something to exist there. And because signals from inside the horizon cannot escape, there is no direct way to test what the singularity is like. And this forces scientists to rely on indirect reasoning and mathematical consistency. And some theoretical approaches suggest that singularities may be smoothed out by quantum effects, replacing infinite densities with extremely high but finite values. And if this is the case, then the interior of a black hole may contain a region of ultra-dense matter rather than an infinitely small point. And while these ideas remain speculative, they share the implication that the singularity predicted by classical theory is likely not the final word. And in this sense, the singularity does not tell us what black holes contain, but rather highlights what we do not yet understand. And it marks a deep intersection between gravity, quantum physics, and the nature of spacetime itself.
The size of a black hole is closely related to its mass, and this relationship helps clarify why black holes can vary so widely in their physical effects. And the boundary of a non-rotating black hole, known as the Schwarzschild radius, increases in direct proportion to mass, meaning that if the mass doubles, the radius of the event horizon also doubles. And this simple scaling has important consequences because it means that more massive black holes have larger horizons and gentler gravitational gradients at the boundary, while smaller black holes have smaller horizons and steeper gradients. And one result of this is that tidal forces at the event horizon can be extreme for small black holes and relatively mild for very large ones. And this explains why the experience of approaching a black hole depends strongly on its mass, and it also means that black holes are not uniformly dense objects because average density decreases as mass increases. And a supermassive black hole can have an average density lower than that of water, even though its central region involves extreme curvature. And this counterintuitive result arises because mass is spread over a much larger volume, and yet despite these differences, all black holes share the same fundamental structure, defined by an event horizon and an interior region from which signals cannot escape. And from an external viewpoint, black holes of different masses behave in similar ways, differing mainly in scale. And this scale-invariant behavior suggests that whatever black holes hide may follow similar principles across a wide range of sizes. And understanding the relationship between mass and size provides a foundation for distinguishing different classes of black holes, which we will explore next, while keeping in mind that differences in scale do not change the basic nature of the boundary between the observable and the hidden. Black holes are often grouped into categories based on their mass, and these categories help organize observations and guide theories about how black holes form and evolve. And the most common type is known as a stellar mass black hole, which forms from the collapse of a massive star. And these black holes typically have masses ranging from a few times the mass of the Sun to several tens of times the Sun's mass, and they are scattered throughout galaxies, often found in binary systems where they orbit a companion star. And in these systems, matter can be transferred from the companion to the black hole, producing detectable radiation.
And another category is known as intermediate mass black holes, which have masses between hundreds and hundreds of thousands of solar masses. And evidence for these objects has been growing, though their formation pathways are still not fully understood. And they may represent building blocks in the growth of larger black holes. And the largest category is supermassive black holes, which reside at the centers of most galaxies, including our own. And these objects can contain millions or billions times the mass of the Sun, and their presence influences the motion of stars and gas across entire galactic regions. And despite their enormous differences in mass, all of these black holes are described by the same underlying physical principles, and their external behavior is determined by mass, rotation, and charge. And this uniformity suggests that whatever black holes hide internally may follow similar rules across all size scales, even though the paths that lead to their formation differ. And recognizing these categories helps place individual black holes within a broader cosmic context and prepares us to examine how black holes are connected to the structure and evolution of galaxies themselves. At the centers of most large galaxies lies a supermassive black hole. And this fact suggests a deep connection between black holes and the formation of galaxies themselves. And observations show that the mass of a galaxy's central black hole is closely related to the mass and motion of stars in the galaxy's central region. And this correlation implies that black holes and galaxies grow together over cosmic time. And one reason for this connection is that gas flowing toward the center of a galaxy can feed the black hole, while energy released near the black hole can influence how gas behaves on much larger scales. And when a supermassive black hole actively accretes matter, it can produce intense radiation and powerful outflows that heat surrounding gas and sometimes push it outward. And this feedback can slow or regulate star formation, shaping the long-term evolution of the galaxy. And in this way, black holes are not merely passive containers, but active participants in cosmic structure. And yet, despite their large-scale influence, the internal regions of these black holes remain hidden behind event horizons. And the same boundary that conceals stellar mass black holes also conceals supermassive ones. And this means that the hidden interiors of black holes exist at the heart of many galaxies, quietly shaping their environments through gravity while remaining observationally inaccessible. And understanding this dual role as both central engines of galactic activity and sealed regions of spacetime highlights how black holes combine outward influence with inward concealment. And this combination deepens the question of what is happening inside objects that play such a central role in the visible universe.
Because black holes do not emit light of their own, their presence must be inferred through their effects on surrounding matter and radiation. And over time, astronomers have developed several methods for detecting black holes using indirect observations. And one of the earliest methods involves studying the motion of stars and gas, because objects orbiting an unseen massive center can reveal the presence of a compact, heavy object through their speeds and trajectories. And in some systems, stars move so rapidly and within such small regions that only a black hole can account for the observed gravity. And another important method involves observing radiation from hot gas in accretion disks,
because as matter spirals inward and heats up, it emits X-rays and other high-energy light. And these emissions often show rapid fluctuations and characteristic patterns that match predictions for matter orbiting near a black hole. And gravitational waves provide yet another way to detect black holes, because when two black holes merge, they produce ripples in space-time that can be measured by sensitive instruments. And these signals carry information about the masses and spins of the merging objects. And although none of these methods allow us to see inside the event horizon, together they provide strong evidence that black holes exist and behave as predicted by theory. And in this sense, black holes are known through their shadows rather than their contents. And the fact that we can confirm their existence without accessing their interiors highlights an important theme, that black holes hide their internal structure while revealing their presence through external influence. And this balance between concealment and detection shapes how we study these objects and sets the stage for deeper questions about what information may or may not be permanently hidden.
Although black holes themselves cannot be seen directly, it is possible to observe the regions immediately around them, and these observations provide valuable clues about the geometry of space-time near the event horizon. And one of the most striking examples is the imaging of a dark region surrounded by glowing material, often called a black hole shadow. And this shadow is not the black hole itself, but a silhouette created by light being strongly bent and captured by gravity. And light from hot gas in the accretion disk is distorted as it passes near the horizon, producing a bright ring around a central dark area. And the size and shape of this ring can be compared with theoretical predictions. And so far, these comparisons show strong agreement with general relativity. And this agreement strengthens confidence in our understanding of black hole boundaries, even though the interior remains inaccessible. And these images also reinforce the idea that black holes hide information not by blocking light with a physical surface, but by shaping the paths that light can take. And in addition to imaging, astronomers study time variations in brightness and polarization of light near black holes, because these patterns reflect motion in strong gravitational fields. And by analyzing such signals, scientists can infer how matter behaves just outside the horizon. And while these techniques cannot reveal what lies inside, they allow us to map the edge of the hidden region with increasing precision. And in this way, observation gradually sharpens the boundary between the known and the unknowable, even as the interior remains beyond reach.
Although black holes themselves cannot be seen, their influence extends outward in ways that leave measurable traces, and these traces allow astronomers to study black holes as physical objects rather than purely theoretical constructs. And one important approach involves measuring how fast matter orbits near the black hole, because orbital speed increases as gravity strengthens, and extremely high orbital speeds indicate a very compact and massive central object. And another approach involves studying how radiation changes over time, because matter near a black hole experiences turbulent motion, producing flickering patterns that can be analyzed statistically. And these patterns reveal characteristic timescales that depend on the black hole's mass. And polarization measurements of light provide additional information, because they reflect the orientation of magnetic fields and the geometry of space-time near the horizon.
And together, these observations create a consistent picture of black holes as predicted by general relativity. And yet all of these techniques operate outside the event horizon, and none can directly probe the interior. And this reinforces a central theme, that black holes are objects whose external behavior is increasingly well understood, while their internal state remains fundamentally hidden. And this separation between external knowledge and internal mystery is not a temporary technical limitation, but appears to be built into the structure of space-time itself. And recognizing this helps clarify why black holes occupy a special place in physics, not simply as difficult objects to observe, but as objects that place a principled limit on observation.
Around many black holes exists a rotating structure known as an accretion disk. And this disk forms because infalling matter almost always carries some sideways motion, meaning it cannot fall straight inward. And as this gas and dust spiral closer to the black hole, internal friction and turbulence cause energy to be released. And this released energy heats the material to extremely high temperatures, often reaching millions of degrees. And at these temperatures, the matter becomes a hot plasma that emits large amounts of radiation, especially in X-rays. And this radiation is one of the primary ways astronomers detect black holes, even though the black holes themselves emit no light. And it is important to note that this brightness does not come from inside the event horizon, but from matter orbiting just outside it. And within the disk, magnetic fields play a central role because they help transfer angular momentum outward, allowing some material to gradually move inward. And without this magnetic transport, matter would remain trapped in orbit. And as gas continues to lose energy and angular momentum, it drifts closer to the horizon, entering progressively stronger gravitational and relativistic conditions. And in some systems, a portion of this energized material is redirected into narrow, focused streams called jets, which emerge along the black hole's rotation axis. And these jets can travel enormous distances, far beyond the size of the black hole and its disk, carrying energy into interstellar and intergalactic space. And although disks and jets are dramatic and energetic, they represent only the final visible stages of matter before it crosses the event horizon. And once matter passes beyond that boundary, it can no longer produce observable radiation. And from the outside, its detailed structure and motion are lost, leaving only a small increase in the black hole's mass and a possible change in its rotation. And this process illustrates a recurring pattern where complex external activity leads to a simple internal accounting, reinforcing how black holes conceal detailed physical histories while retaining only a few measurable properties. Strong magnetic fields are an essential part of the environment around many black holes. And although magnetic fields cannot be seen directly, their presence quietly shapes how matter moves, how energy is transferred, and how radiation is produced in the surrounding region. And near a black hole, magnetic field lines become dragged, twisted, and stretched by the motion of the accretion disk. And this slow twisting stores energy inside the magnetic field itself. And over time, this stored energy can be released in controlled ways, gently heating nearby plasma
and accelerating charged particles. And magnetic fields also play an important role in moving angular momentum through the disk, allowing some material to drift inward while other material moves outward. And without this magnetic transport, much of the gas would remain trapped in orbit rather than slowly spiraling toward the horizon. And in addition to shaping the disk, magnetic fields are closely connected to the formation of jets, because they can guide streams of charged particles into narrow, organized flows along the black hole's rotation axis. And these jets can extend far beyond the immediate surroundings of the black hole, carrying energy into interstellar and even intergalactic space. And although jets appear dramatic when imaged, their underlying mechanism is gradual and continuous, driven by the steady interaction between rotation, gravity, and magnetic structure. And all of these processes occur outside the event horizon, where information can still escape and be measured. And yet they strongly influence what eventually crosses the horizon, because magnetic fields regulate how quickly matter falls inward and how much energy is released beforehand. And from an observational perspective, magnetic activity affects the brightness, timing variations, and polarization of light near black holes. And by studying these subtle signals, astronomers can infer the presence and behavior of magnetic fields even without directly observing them. And despite this growing knowledge of black hole environments, magnetic fields cannot reveal what happens once matter passes beyond the horizon. And this limitation remains absolute. And in this way, magnetic fields illustrate a broader pattern, where increasingly detailed knowledge is available at the edge of the black hole, while the interior remains sealed off. And understanding this boundary between accessible physics and hidden physics prepares us to examine deeper questions about what may happen to information once it crosses into the black hole. Because black holes do not emit light of their own, their presence must be inferred through their effects on surrounding matter and radiation. And over time, astronomers have developed several methods for detecting black holes using indirect observations. And one of the earliest methods involves studying the motion of stars and gas, because objects orbiting an unseen massive center can reveal the presence of a compact, heavy object through their speeds and trajectories. And in some systems, stars move so rapidly and within such small regions that only a black hole can account for the observed gravity. And another important method involves observing radiation from hot gas in accretion disks, because as matter spirals inward and heats up, it emits X-rays and other high-energy light. And these emissions often show rapid fluctuations and characteristic patterns that match predictions for matter orbiting near a black hole. And gravitational waves provide yet another way to detect black holes, because when two black holes merge, they produce ripples in space-time that can be measured by sensitive instruments. And these signals carry information about the masses and spins of the merging objects. And although none of these methods allow us to see inside the event horizon, together they provide strong evidence that black holes exist and behave as predicted by theory. And in this sense, black holes are known through their shadows rather than their contents. And the fact that we can confirm their existence without accessing their interiors highlights an important theme: that black holes hide their internal structure while revealing their presence through external influence. And this balance between concealment and detection shapes how we study these objects and sets the stage for deeper questions about what information may or may not be permanently hidden.
One theoretical prediction that plays a central role in discussions about black holes and information is known as Hawking radiation. And this effect arises when quantum physics is applied to the region very close to the event horizon. And according to this idea, black holes are not perfectly black, but instead emit a very small amount of radiation over extremely long periods of time. And this radiation does not come from inside the black hole, but from the space just outside the horizon itself, where quantum fluctuations are always occurring. And in quantum theory, empty space is not truly empty, but filled with brief fluctuations in which pairs of particles appear and disappear. And under ordinary conditions, these pairs annihilate almost immediately, leaving no lasting trace. And near the event horizon, however, it is possible for one particle from such a pair to fall into the black hole while the other escapes. And when this happens, the escaping particle appears as radiation, while the black hole loses a tiny amount of mass. And this slow leakage of energy means that black holes gradually shrink over time. And for stellar mass and supermassive black holes, this process is incredibly slow, far slower than the current age of the universe. And yet, the theoretical consequences are significant because it suggests that black holes are not permanent, but temporary objects on very long timescales. And if a black hole can slowly evaporate, this raises a deep question about what happens to the information associated with everything that has fallen into it. And in the simplest interpretation of Hawking radiation, the emitted particles appear random, carrying no detailed imprint of the black hole's interior. And if this were truly the case, then when a black hole eventually disappears, the information about its contents would be lost forever. And this would directly conflict with a core principle of quantum mechanics, which states that information is never destroyed. And because of this conflict, many physicists believe that Hawking radiation must contain extremely subtle correlations that encode information, even if those correlations are far beyond our current ability to measure. And in this view, the radiation is not truly random, but only appears random when examined in a limited way. And this possibility suggests that information may slowly leak back into the universe in an encoded form, rather than remaining permanently hidden. And at present, there is no experimental way to test these ideas, and they remain within the domain of theoretical research. And this uncertainty means that Hawking radiation does not yet tell us exactly what black holes hide, but it strongly suggests that the boundary of a black hole is not a simple one-way sink, and instead may play an active role in how information is processed. And this quiet possibility reshapes how we think about black holes, not as perfect erasers, but as complex systems whose deepest behavior is still unfolding within our understanding. When black holes slowly emit Hawking radiation, they lose an extremely small amount of mass, and this gradual loss implies that black holes change over time, even when they are isolated from their surroundings. And although this change is far too slow to observe directly for astrophysical black holes, it has important conceptual implications because it suggests that black holes are not static containers, but evolving systems. And as a black hole loses mass, its event horizon slowly shrinks, and the conditions near the horizon gradually change. And this slow evolution raises questions about how information might be carried outward during evaporation,
and whether the outgoing radiation can, in principle, encode details about what previously fell inside. And one way to think about this is to imagine the black hole as storing information in a highly scrambled form, and then releasing that information extremely slowly through subtle patterns in the emitted radiation. And in this picture, nothing dramatic occurs at any moment, but over immense spans of time, the black hole gradually returns its information to the surrounding universe. And this idea aligns with the principle that information is never destroyed, but it also stretches that principle into regimes far beyond ordinary experience. And it is important to note that evaporation is not expected to proceed at a constant rate, because as the black hole becomes smaller, its temperature increases, and this causes the rate of radiation emission to rise. And near the final stages, the process may accelerate, though the exact behavior is not yet known. And this uncertainty reflects the fact that a complete theory of quantum gravity does not yet exist. And without such a theory, we cannot reliably describe the final moments of black hole evaporation. And this means that some of the most important questions about black holes remain unanswered, including whether a final remnant remains or whether the black hole disappears completely. And these possibilities lead to different conclusions about how information is ultimately handled. And regardless of which scenario is correct, the slow evaporation of black holes suggests that what they hide may not be hidden forever, but rather hidden for timescales that vastly exceed the age of stars, galaxies, and perhaps even the current universe itself. And this long-term perspective reframes black holes from eternal prisons into extremely slow processors of matter, energy, and information.
Black holes are also closely connected to a concept known as entropy, which in physics is a measure of how many microscopic arrangements correspond to a system's overall state. And higher entropy generally means greater disorder or greater hidden complexity. And ordinary objects have entropy because their particles can be arranged in many different ways, even when the object appears unchanged at large scales. And black holes, despite their simple external appearance, possess enormous entropy, far greater than that of ordinary matter with the same mass. And this result emerges from theoretical work showing that the entropy of a black hole is proportional to the area of its event horizon rather than its volume. And this relationship is unusual because it suggests that the information content of a black hole is somehow associated with its surface, not its interior. And this idea has profound implications because it hints that the fundamental description of nature may involve information being stored on boundaries rather than within regions of space. And this surface-based view is sometimes called the holographic principle. And while the details of this principle are still being explored, it provides a possible framework for understanding how black holes could store vast amounts of information without violating physical laws. And in this picture, the event horizon is not merely a passive boundary, but a structure that encodes information about what is falling inside. And yet, from the outside, this information is not directly accessible and can only influence observations in extremely indirect ways. And the connection between entropy and horizon area also links black holes to thermodynamics, the branch of physics that studies heat, energy, and entropy. And this connection suggests that black holes behave in some respects like thermal objects with a temperature and entropy, even though they are formed from gravity.
And this blending of gravity, quantum theory, and thermodynamics highlights how black holes sit at the crossroads of fundamental physics. And understanding black hole entropy provides another perspective on what black holes hide, not as simple empty voids, but as systems containing vast amounts of encoded information.
Inside a black hole, the structure of space and time is predicted to become extremely distorted. And while we cannot directly observe this region, theoretical models provide some insight into how space-time may behave. And in general relativity, space-time curvature increases as one moves inward, meaning that distances and durations lose their familiar meanings, and directions that once represented ordinary space begin to behave more like directions in time. And this leads to a situation where movement toward the center becomes unavoidable, much like the passage of time outside a black hole. And this conceptual shift helps explain why nothing can remain stationary inside the horizon. And another consequence of strong curvature is that the separation between events becomes increasingly compressed, and the idea of a stable spatial structure gradually fades. And instead, the interior can be thought of as a dynamic region where change is constant and inevitable. And some theoretical descriptions suggest that space-time inside a black hole may become highly anisotropic, meaning that different directions behave very differently. And this anisotropy can amplify stretching and compression effects on matter and fields. And quantum effects are also expected to become important in these regions because extreme curvature corresponds to extremely high energies at small scales. And this combination of strong gravity and quantum behavior is precisely where current theories become incomplete. And as a result, any description of the deep interior must remain tentative. And what can be said with confidence is that the interior of a black hole is not an ordinary place with ordinary geometry, but a region where the fundamental structure of space-time itself departs from everyday intuition. And this departure is a key part of what black holes hide, because it represents a domain where our most basic concepts of space and time may no longer apply.
Near the deepest regions of a black hole, quantum effects are expected to play an increasingly important role because the energies and densities involved approach scales where quantum behavior becomes unavoidable. And while a complete theory of quantum gravity does not yet exist, physicists use partial frameworks to explore how quantum processes might modify the classical picture. And one possibility is that quantum fluctuations of space-time become significant, meaning that geometry itself may undergo small, rapid variations rather than remaining smooth and continuous. And this would represent a fundamental shift from the assumptions of general relativity. And such fluctuations could soften the extreme conditions predicted by classical theory, preventing the formation of true infinities, and instead producing a region of very high but finite curvature. And another idea is that matter inside a black hole may enter exotic quantum states, where particles are strongly entangled and cannot be described independently. And this entanglement could play a role in how information is stored or redistributed. And some approaches suggest that the interior of a black hole may not be a simple three-dimensional region, but may involve additional effective dimensions or emergent structures that arise from underlying quantum relationships.
And while these ideas differ in detail, they share the theme that quantum physics likely alters the classical image of a singular core and replaces it with a more complex and subtle interior. And it is important to emphasize that these are theoretical explorations rather than established facts, and their value lies in pointing toward possible directions for future understanding. And taken together, these ideas suggest that what black holes hide may not be a simple endpoint of collapse, but a domain of unfamiliar quantum space-time behavior that challenges our deepest assumptions about reality.
Several theoretical models attempt to describe what the internal structure of a black hole might be once quantum effects are taken seriously. And although none of these models can yet be tested by observation, they offer structured ways of thinking about how collapse could proceed without producing the infinite densities predicted by classical theory. And one group of ideas suggests that as matter collapses inward, it reaches an extreme but finite density, where further compression becomes impossible, forming a compact core rather than a true singularity. And in this view, gravity is balanced at very small scales by quantum effects that resist complete collapse. And another group of models proposes that the interior of a black hole is not best described as a static object at all, but as a dynamic region where space-time itself changes character, transitioning into a new phase governed by different physical rules. And in such descriptions, the familiar distinction between spatial directions and time-like directions becomes blurred, and the idea of a central point loses its usual meaning. There are also speculative models in which collapse leads to a bounce, where matter reaches a minimum size and then begins to expand again, potentially forming a new region of space-time that remains causally disconnected from our universe. And while this idea is sometimes described as a new universe forming inside a black hole, it is important to treat this as a mathematical possibility rather than an established physical claim. And across all of these approaches, a common theme appears: that the singularity predicted by classical general relativity is likely not a literal feature of nature, but a signal that the theory has reached its limit, and that quantum principles must take over at very small scales. And even if these internal structures exist, they remain hidden behind the event horizon, meaning that no information about their detailed behavior can be sent back to the outside universe. And this preserves the black hole's defining role as a boundary of access. And from the outside, all of this potential internal complexity is reduced to a few simple observable properties. And this contrast between deep internal richness and external simplicity is not a flaw in our description, but a fundamental aspect of how black holes operate. And recognizing this helps clarify that when we ask what black holes hide, we are not asking about a single object or structure, but about an entire domain of physics that remains beyond direct observation, yet continues to shape how we think about gravity, quantum theory, and the nature of space-time itself.
Some ideas in theoretical physics suggest that black holes may be connected, at least mathematically, to structures known as wormholes. And wormholes are hypothetical configurations of space-time that link distant regions through a shortened geometric path. And these ideas arise from certain solutions to the equations of gravity, where black hole geometries and wormhole geometries share closely related mathematical forms. And this resemblance has led researchers to explore whether the interior of a black hole might, in some cases, be described using wormhole-like language. And it is important to state calmly and clearly that this does not mean black holes are known to function as usable tunnels, and there is no evidence that anything can pass through a black hole and emerge somewhere else. And in most theoretical treatments, any wormhole-like structure associated with a black hole would be unstable, short-lived, or non-traversable, meaning that nothing could travel through it and return. And these models are therefore not about transportation, but about understanding possible internal geometries. And one reason these ideas attract attention is that they highlight how flexible space-time geometry can be under extreme conditions. And gravity does not restrict space-time to a single simple shape, but allows many mathematically consistent arrangements. And some modern approaches go further and suggest a relationship between wormhole-like geometry and quantum entanglement, which is a form of deep correlation between particles that persists even when they are far apart. And in these approaches, space-time connections may emerge from underlying quantum relationships rather than existing as independent structures. And while this line of research is highly abstract, it reflects an important shift in how physicists think about space itself, moving from space as a background stage to space as something that may arise from deeper processes. And if such ideas are correct, then the interior of a black hole may not resemble a simple hollow region or a single central point, but a more complex geometric arrangement shaped by quantum structure. And yet, even in these models, the event horizon continues to function as a strict boundary, and no signal from inside can reach the outside universe. And this means that wormhole-related ideas do not weaken the conclusion that black holes hide their interiors, but instead broaden the range of possibilities for what that hidden interior might be. And in this sense, wormholes do not provide escape routes, but serve as conceptual tools for exploring how extreme gravity and quantum physics might shape space-time in unfamiliar ways.
Even with many theoretical ideas about what the interior of a black hole might be like, it is important to clearly recognize the limits of current models, because every existing description relies on approximations and incomplete frameworks. And while general relativity provides an extremely accurate description of gravity in most environments, it does not include quantum effects. And while quantum mechanics provides an extremely accurate description of particles and fields, it does not include gravity in a complete way. And black holes exist precisely at the intersection of these two domains, where both gravity and quantum behavior become equally important. And because a fully developed theory of quantum gravity does not yet exist, any description of the deep interior must remain uncertain. And this uncertainty is not a small technical detail, but a fundamental limitation of present-day physics. And it means that physicists cannot yet say with confidence whether singularities truly exist, whether they are replaced by ultra-dense quantum cores, or whether space-time itself changes into a different phase inside black holes. And instead of one accepted picture, there exists a wide landscape of competing models, each motivated by certain mathematical or conceptual principles, but none confirmed by direct evidence. And this situation can feel unresolved, but it reflects an honest boundary of knowledge rather than a flaw in scientific reasoning.
And it also highlights an important feature of science, that unanswered questions are not signs of failure, but markers of where deeper understanding is needed. And black holes, therefore, serve as natural laboratories for probing the foundations of physics, even though their interiors cannot be directly accessed. And in this sense, black holes do not merely hide matter and energy, but also hide information about the ultimate structure of physical law. And when scientists explore black holes' interiors through theory, they are not trying to build imaginative stories, but to test which mathematical frameworks remain consistent under the most extreme conditions imaginable. And over time, some of these frameworks may be ruled out, while others may point toward a more complete theory. And this slow filtering process is how physics advances. And recognizing these limits helps keep our exploration grounded, because it reminds us that the mystery of black holes is not a single unanswered question, but a collection of interconnected problems spanning gravity, quantum mechanics, space-time, and information. And understanding that these limits exist prepares us to approach the remaining parts of this journey with patience and careful attention.
Even though we cannot observe the interior of a black hole directly, physicists use computer simulations to explore how matter, energy, and space-time behave under extreme gravitational conditions. And these simulations combine equations from general relativity, fluid dynamics, and electromagnetism to model how black holes interact with their surroundings. And by adjusting parameters such as mass, rotation, and magnetic field strength, researchers can study how different types of black holes might evolve and how their environments might appear to distant observers. And these simulations are especially valuable because they allow scientists to test theoretical ideas in a controlled setting, comparing simulated predictions with real astronomical data. And when simulations successfully reproduce observed features, such as accretion disk shapes, jet structures, and brightness variations, confidence in the underlying physical models increases. And although simulations cannot reveal what happens beyond the event horizon, they help constrain which theoretical descriptions of the interior are consistent with external behavior. And in this way, even indirect modeling can eliminate some possibilities. And over time, improvements in computing power and numerical methods have allowed simulations to become increasingly detailed, capturing turbulent motion, magnetic instabilities, and relativistic effects with greater accuracy. And this growing realism helps bridge the gap between abstract equations and observable phenomena. And it also highlights a quiet but important point, that much of our knowledge about black holes comes not from direct observation, but from carefully constructed inference. And this reliance on inference does not weaken the conclusions, but reflects the nature of studying objects that place fundamental limits on observation. And through simulation, scientists can explore how black holes behave as physical systems, even while accepting that their deepest interiors remain hidden. And this approach demonstrates how science continues to make progress even when faced with regions of permanent inaccessibility.
Alongside computer simulations, physicists often use thought experiments to explore the logical consequences of physical laws in extreme situations.
And black holes have inspired some of the most influential thought experiments in modern physics because they push concepts like time, causality, and information to their limits. And a thought experiment does not describe a practical laboratory setup, but rather a carefully defined imaginary scenario used to test whether a theory remains self-consistent. And one classic example involves imagining an observer falling into a black hole while another observer remains far away, and comparing what each observer experiences. And this comparison reveals how different frames of reference can produce very different descriptions without contradiction. And another thought experiment considers what would happen if information were truly destroyed inside a black hole, and whether this would violate fundamental principles of quantum mechanics. And by following the logical implications step by step, physicists can identify where assumptions must be revised. And thought experiments do not provide direct answers, but they clarify which possibilities remain viable and which lead to inconsistencies. And in this way, they function as conceptual filters, narrowing the range of acceptable theories. And black holes are especially well suited to this approach because they combine well-understood external behavior with deeply uncertain internal structure. And this contrast allows researchers to isolate where knowledge is solid and where it becomes speculative. And over time, many ideas about black holes have been refined or abandoned based on the outcomes of thought experiments. And this quiet process of elimination plays an important role in scientific progress, and it reinforces the idea that even when direct observation is impossible, careful reasoning can still reveal meaningful constraints. And through thought experiments, black holes continue to shape how physicists think about the deepest rules governing reality.
When scientists consider what it might be like to fall into a black hole, they are not attempting to create dramatic imagery, but rather to carefully trace how known physical laws would influence a body and its measurements along such a path. And in theoretical descriptions, an observer falling freely toward a sufficiently large black hole would experience a gradual and continuous change in gravitational conditions, rather than any sudden transition. And far from the black hole, motion, weight, and the passage of time would feel ordinary, while closer in, tidal forces would slowly increase as differences in gravitational pull across the body become more noticeable, and clocks carried by the falling observer would continue to tick at a normal rate from their own perspective. And this means that crossing the event horizon itself would not feel like striking a surface, entering a tunnel, or passing through a visible boundary, but like moving through an unmarked region of space. And this quietness is one of the most counterintuitive features of black holes, because the horizon represents such a profound limit from the outside, yet locally it does not announce itself. And as the observer continues inward beyond the horizon, tidal forces would continue to grow, and stretching along the direction toward the center, and compression in sideways directions would gradually become stronger. And at some point, depending on the mass of the black hole, these forces would become intense enough to disrupt biological tissue and eventually break down atomic structures.
And this destructive process would not occur instantly, but would unfold progressively as the gravitational gradient increases. And from the outside universe, none of these internal changes could ever be observed, because signals emitted from inside the horizon cannot escape. And this creates a permanent separation between what is experienced inside and what can be known outside. And this separation illustrates once more that black holes hide sequences of events rather than simply swallowing objects whole. And although these descriptions are grounded in well-tested physics outside the horizon, they become increasingly uncertain as one approaches the deepest regions, where quantum effects are expected to dominate. And for this reason, any description of the final stages of infall must remain provisional. And this careful uncertainty is not a weakness, but an honest reflection of where present-day theory reaches its limits.
An important question that naturally follows from considering infall is whether anything that enters a black hole can ever escape. And within the framework of classical general relativity, the answer is no, because once an object crosses the event horizon, all possible future paths lead inward, and no trajectory exists that allows return to the outside universe. And this statement applies not only to material objects, but also to light. And because light cannot escape, no signal can be sent from inside the horizon to the outside. And this one-way structure defines the black hole as a region of permanent causal separation. And it is important to understand that this restriction does not arise from an outward force acting as a barrier, but from the geometry of space-time itself, which shapes the set of possible paths. And even powerful propulsion or advanced technology would not change this outcome, because motion is constrained by the underlying structure of space-time rather than by engine strength. And this conclusion is one of the most robust predictions of general relativity, and it holds regardless of the details of what lies deeper inside. And in quantum theory, the situation becomes more subtle because Hawking radiation allows energy to slowly escape from the region near the horizon. And this introduces a limited sense in which black holes are not completely sealed. And yet, Hawking radiation does not provide a channel for material objects or organized signals to escape from inside. And it does not allow an observer who has crossed the horizon to return. And in this sense, black holes remain effectively inescapable. And this inescapability plays a central role in why black holes hide their interiors so completely. Because hiding is not achieved through concealment in space, but through absolute restriction in time and causality. And understanding this prepares us to consider what ultimately happens to matter and information that cannot return.
When matter crosses the event horizon, it does not vanish from existence, but it also no longer remains part of the observable universe. And this distinction is subtle yet deeply important, because it shifts the question from disappearance to inaccessibility. And from the outside, all that can be measured is that the black hole's mass, rotation, and sometimes charge have changed slightly, while the detailed identity of the infalling matter is no longer available to observation. And this leads to the idea that black holes reduce complex inputs into very simple external descriptions. And this simplification is one of their most characteristic features. And from a physical standpoint, the mass and energy carried by infalling matter continue to contribute to the black hole's gravitational field, and therefore continue to influence the motion of nearby stars, gas, and radiation.
And in this sense, matter that falls into a black hole still shapes the universe, even though its internal state cannot be examined. And deeper inside, theoretical descriptions suggest that matter does not freeze or remain static, but continues to evolve under extreme conditions, undergoing ongoing compression, heating, and transformation. And these processes are governed by physical laws, even if we cannot currently describe them in complete detail. And one way to think about this is that black holes do not act as cosmic erasers, but as extreme processors, taking in structured matter and converting it into an internal state that is highly compressed and highly scrambled. And this internal processing is hidden from view, but not necessarily meaningless. And this perspective connects naturally to ideas about information conservation, because if information is not destroyed, then it must persist in some encoded form, even if it cannot be accessed or reconstructed. And at present, we do not know what that encoding looks like, or where it is located, or how it is represented physically. And yet the possibility that matter and information persist inside black holes challenges simple narratives of total annihilation, and instead suggests a quieter picture where transformation replaces destruction. And in this picture, black holes are not places where reality ends, but places where reality becomes unreachable. And this unreachable state is central to what black holes hide, because it represents a boundary not only in space, but in knowledge. And recognizing this helps shift the question away from dramatic images of disappearance and toward a more careful consideration of what it means for something to exist without being observable. And this distinction will remain important as we move toward the final parts of the series, where we consider the ultimate fate of matter and information in a universe that contains black holes.
Over very long periods of cosmic time, black holes influence not only their immediate surroundings, but also the large-scale evolution of matter in the universe. And although they are relatively small compared to galaxies, their gravitational and energetic effects can shape how matter is distributed. And when black holes grow by accreting gas and stars, they lock significant amounts of matter into regions that are no longer accessible to the rest of the universe. And this gradual sequestration changes where matter resides and how it participates in future processes. And at the same time, black holes also release energy through radiation from accretion disks and through jets. And this energy can heat surrounding gas, preventing it from cooling and forming new stars. And in this way, black holes can slow down or regulate star formation on galactic scales. And this combination of locking matter away and injecting energy outward gives black holes a subtle but persistent role in shaping cosmic evolution. And when we consider the fate of matter that enters black holes, we are therefore also considering the long-term fate of matter in the universe as a whole. And if black holes eventually evaporate through Hawking radiation, then matter and energy may slowly return to the wider universe in highly dispersed forms. While if they do not fully evaporate, then a portion of the universe's matter may remain permanently hidden. And both possibilities have different implications for the distant future. And although we do not yet know which scenario is correct, the presence of black holes ensures that some fraction of matter spends extremely long periods in states that are inaccessible to ordinary processes. And this deep timescale emphasizes that black holes are not merely dramatic endpoints, but long-term participants in cosmic change. And understanding this broader context helps place the hidden interiors of black holes within the larger story of how the universe evolves. When we consider the fate of information in the presence of black holes, we are not only asking about individual objects, but about the consistency of physical law across the entire universe. And if information can truly be destroyed, then the universe would contain processes that erase history in an irreversible way. While if information is always preserved, then even the most extreme environments must encode past states in some form. And black holes force this question into sharp focus, because they combine extreme gravity with apparent loss of accessible detail. And one possible view is that information is preserved but becomes so thoroughly scrambled that it is effectively unrecoverable, even though it still exists in principle. And another view is that information is stored at the event horizon in a distributed way, rather than being localized deep inside. And a third view is that information slowly leaks out through subtle correlations in Hawking radiation over immense timescales. And all of these ideas attempt to reconcile the behavior of black holes with the principles of quantum mechanics, and none have yet been confirmed. And this lack of confirmation does not imply that the problem is unsolvable, but rather that it lies at the frontier of theoretical physics. And the persistence of this question over decades reflects its depth, because it touches not only on black holes, but on the nature of time, causality, and physical law itself. And in this sense, black holes hide more than matter and energy. They hide clarity about whether the universe is fundamentally reversible or fundamentally lossy. And recognizing this broad significance helps explain why black holes occupy such a central place in modern physics, even though their interiors remain observationally sealed.
After exploring how black holes form, how their boundaries behave, how matter and energy interact with them, and how information may be affected, we arrive at a quiet but important realization that black holes do not offer a single simple answer to the question of what they hide, and instead reveal layers of partial understanding and persistent uncertainty. And at one level, black holes hide regions of space-time that are causally disconnected from the rest of the universe, meaning that whatever happens there cannot influence distant observers. And at another level, they hide the limitations of our current theories, because the deepest interior lies beyond the reach of both general relativity and quantum mechanics as they are presently formulated. And at yet another level, black holes hide potential clues about a deeper unifying framework that may one day connect gravity, quantum physics, and information into a single coherent description. And this layered nature of hiding is important because it shows that black holes are not simply mysterious objects, but markers of where knowledge transitions into open questions. And throughout this exploration, we have seen that black holes are shaped by ordinary physical processes, such as stellar collapse and galactic growth, and yet they lead to extraordinary consequences for space, time, and causality. And this combination of familiarity and extremity is what makes them such powerful subjects of study. And while we cannot yet say what the deepest interior of a black hole is like, we can say with confidence that black holes do not represent simple holes in space, but structured regions governed by physical law, even if those laws are not yet fully known. And in this sense, what black holes hide is not an absence, but a frontier, a boundary between what is understood and what remains to be discovered. And approaching this frontier with patience and careful reasoning is the essence of scientific progress. And as we move toward the final part, we will step back slightly and reflect on why black holes continue to fascinate, not only as astronomical objects, but as guides to the deepest questions about reality.
Black holes continue to fascinate because they provide not dramatic answers, but because they quietly expose the limits of what can be known. And in doing so, they shape how we think about the universe at its most fundamental level. And they show us that reality is not fully accessible from any single viewpoint, and that observation itself is constrained by the structure of space-time. And black holes also demonstrate that simple external appearances can hide immense internal complexity, and that physical systems can be both well described and deeply mysterious at the same time. And throughout this series, we have seen that black holes emerge naturally from the same laws that govern stars and galaxies, and yet lead to conditions where those laws begin to strain. And this tension is not a sign of failure, but a sign that deeper principles remain to be discovered. And in this sense, black holes serve as quiet guides toward future theories, pointing not through spectacle, but through consistency and persistence. And although we may never directly observe what lies beyond an event horizon, we can continue to refine our understanding of black holes by studying their effects, testing our theories, and examining where those theories succeed and where they break down. And this process reflects the broader nature of science, where progress often comes not from final answers, but from clearer questions. And black holes, more than almost any other objects, embody this process, because they sit at the boundary between the known and the unknown, and invite us to explore that boundary with patience, humility, and careful thought. And in doing so, they remind us that what is hidden is not separate from what is known, but is part of the same continuous effort to understand the universe more deeply.
As we come to the end of this session, there's nothing you need to take with you. No ideas to hold on to. No thoughts to finish. The words can fade, just like the day slowly does. If you found this space calming, you can leave a like or subscribe to the channel. It quietly supports more moments like this. For now, let everything settle. You don't need to listen closely anymore. The sound can stay even as attention drifts away. Rest easy and let time continue gently on its own.